All right, and so we're back. Let's just recap that our new goal is to examine two different populations. And when we have two different populations, we're still going to go by that approach where our first question is going to be, are we interested in a qualitative variable or are we interested in a quantitative variable? If we are interested in a qualitative variable, then clearly we're going to be analyzing proportions. For example, the A/B testing, where it was the proportion of, for example, success, however that may be determined. And what we're going to do is we're essentially going to ask, are the proportions equal or not? And that's pretty much it. If you're interested in the difference between them, then that would be a confidence interval. So let's go ahead and get started with the framework. Suppose there are two populations of interest. Here's population one, so we can call this pop one. So you can think of this being the A, right? So every little shape that you see here would essentially be an individual. Could be a person, could be an item, could be a website, could be anything, right? It's your population. If population one is format A, then notice black serves to indicate that the trait or characteristic is present. So this individual here is counted as a success. This individual here counted as a success. However, an individual down here would not be a success. So if, for example, during A/B testing, this is the way the population actually would behave, and we're trying to determine the proportion of success, then this would be P1. Similarly, population 2 would be for the B case. And this gives us P2, which would be 0.3. Obviously, in this case, because we're interested in traits or characteristics, we are looking at qualitative variables. And so it's very natural that we're looking at proportion. You don't have access to the entire population. So one of the first things is gonna be, well, how do these proportions differ? Again, these are not accessible to us. We don't quite yet know that B would, would observe a higher proportion of success for that website. So we're really interested in trying to make some kind of claim regarding P1 versus P2. So the question is P1 the same as P2? Is P1 less than P2? Is P1 greater than P2? Or is P1, right, we have no reason to believe that either would be different. I would argue that it's very natural for the A/B testing a lot of the time. It's very surprising the results that come out of these A/B testing, because why would the color on the buy button matter, right? It doesn't quite make sense from a purchasing standpoint. It makes more sense from a psychological standpoint, kind of like why McDonald's has, the red and gold arches. So that would be more of a psychological question, that people are more comfortable with certain colors. So again, a lot of the time for A/B testing would be P1 not equal to P2 unless there's evidence to the contrary. So here's more or less the logic of the procedure that we will employ. We're going to say, well, we don't know whether there is a difference. So my null hypothesis will be that the proportions are actually the same. And if the proportions are the same, then when I subtract them, P1 minus P2, that should be a value very close to 0. So first, we're going to go ahead and say, well, we don't have access to the population, so we can go ahead and collect a sample from each population. Let's do SRS, simple random sample from each population. And then we're going to go ahead and compute P1 hat and P2 hat. So again, we sampled, and then we're looking at the proportion in our sample. So that would be sample 1. And then we can do the same thing over here. Take some kind of sample. That'll be sample 2. And in those samples, we're essentially saying what is the proportion of success for P1 and what is the proportion of success, essentially our estimates then for P2. Now, if the real proportions are actually equal to each other, then we also expect that the sample proportions should be very close to one another. So we're going to ask, is P1 hat minus P2 hat close to 0? I don't expect this to be exactly 0. I know there's natural variability. So this really gives us the question of, how does this statistic behave? So we need to understand how this behaves, because again, this sort of makes sense that we expect the sample proportion to be different, but we really want it to be small. So at what point, what number would we not consider a number close to 0? And so that really is what we answered way back when we looked at sampling distributions. So now we can do something similar where we're going to say, well, what is the sampling distribution of the difference of the sample proportions of P1 hat minus P2 hat? Luckily, this question is pretty simple because of the central limit theorem. So by the central limit theorem, we know that if our sample sizes N1 and N2 are large enough, then the sampling distribution of the of the difference of the proportions, sample proportions, is 1, gonna be approximately normal. 2, will have a center of, so mu of P1 hat minus P2 hat, it has a center of P1 minus P2. Let me compare that to the sample distribution, the sampling distribution of a single proportion. That was mu of P hat, and we had said that that was just P. But now I have a difference. Okay, so these formulas should look very familiar. Now the standard error when we had a single proportion, assuming my sample size was large enough, was given by P times 1 minus P over N. And in a similar way here, when we have the standard error, we have the square root of P1, 1 minus P1, all over N1, plus P2 times 1 minus P2, all over N2. And if you recall what we did before, we said, well, we don't have these standard errors, but we can definitely estimate. So we're going to go ahead and replace P1 and P2 with their point estimates. And so that basically gives rise to the inference part of this. So I don't want to write out the formulas because we're actually going to be using 0 formulas for this. We've been using StatCrunch, and luckily StatCrunch is formula free. You just need to feed it your sample and tell StatCrunch what kind of test you're trying to perform. So this is the backbone. If you're really curious, these results here are what allow us to continue constructing confidence intervals, finding sample size requirements, as well as performing hypothesis tests on the 2 samples. So let me just go ahead and actually point out how things are going to change when we perform a hypothesis test for 2 samples. So part 1 says you want to determine the parameters you wish to examine. So I am a big fan of this. I always encourage students to write out what P1 is. So what is the population that you're interested in? So this would be the true population proportion of, and then you basically fill in what the trait or characteristic is, as well as more detail as to the population that you're looking at. So it could be, for example, proportion of first-year students who watched, the #1 show on Netflix versus P2, the true population proportion of, and then we can say individuals. I think we had said first year was P1, so maybe P2 could be 4th-year students who have watched the #1 show on Netflix. Then we're going to write the hypothesis. So the hypothesis will always be a no change hypothesis. So we're always going to say P1 is equal to P2. That's going to be your null hypothesis. P1 equals P2. A lot of times we're going to go ahead and write that differently as P1 minus P2 equals 0. These are equivalent. If P1 is the same as P2, then P1 minus P2 is 0. And then we're going to go ahead and compare. So either we want to ask whether this is less than, right? Is P1 less than P2, which will translate to P1 minus P2 being less than 0. So what I want to point out here is that it really doesn't matter which one you write. Just be aware that StatCrunch, I believe, writes it on the right-hand side. So StatCrunch will do the P1 minus P2. So the null hypothesis will always be E equals 0. The alternative, whatever inequality sign or sign you use here, will be the same over here. So that's one difference. Now, checking the requirements for these, we've seen before. Notice that this still uses central limit theorem. So it's the same requirements that we had in the previous chapter. So checking the requirements here, we now have two groups. We have two populations. So we actually have to check these requirements for each sample. So for example, here is population 1. For population 1, we need to make sure that there's a simple random sample. And we need to make sure that we have independence. Remember that independence was shown by the sample size being less than 5% of the population size. So now we see a big N1 to demonstrate that that's the size of population 1. Then we go ahead and verify the shape requirement, which was NP 1 minus P had to be greater than 10. We don't know what P is, so we're going to replace that with my point estimate on P1, and then make sure that you state that this would be N1 because you're looking at population 1. You would repeat the same thing for population 2, because then this would ensure that the sampling distribution for each one was normal. So there is some theory that goes into this, but you just want to ensure that everything that we had stated before, if you treated each population individually, would still apply. So again, now this would be SRS independence from the second sample, which is achieved by having a sample size that's small relative to the population. So now this would be N2. And then finally, we're going to verify the shape requirement. Or I'm going ahead and substituting the fact that we need to use the point estimate, because the null hypothesis doesn't tell me in this case what the proportion is. All right, so just like the previous hypothesis test, these take a while to set up, and we've seen that this is approximately normal. So in class or on assessment, I will ask you to sketch the distribution. And so the same idea holds. We're analyzing proportions, so therefore you're going to sketch a normal distribution and shade the critical region according to the alternative. Oh, this should be H1. I just saw. All right, finally, to get your test statistic, determine the sample statistics, so t-stat and p-value. It's the same as before. We've already seen this. It's stats. These are proportions, so we'll go to prop stats. This time, however, you're going to select two samples because we're dealing with two samples. And usually for proportions, you will select with summary. And that's pretty much it. So if this all sounds familiar, that's a great sign. Now we just need to go ahead and practice actually employing a two-sample hypothesis test.